Hi. Today marks the end of all the shapes and polygons that we've been looking at so far. Instead, we're going to focus on a single shape, the triangle. And you may be saying, well, why the triangle? What's so special about the triangle? Well, that's a great question. Because for thousands of years, people have looked at the triangle and found some very, very unusual, very interesting properties. And those properties have led to so many branches of mathematics that we use all the time. You might say, well, how on earth does a single three-sided shape lead to all those branches of mathematics, besides geometry? Well, that's a great question. And it all starts with this, Pythagorean Theorem. Now, this is a pretty long word, even by the standards of geometry. So, what does this word actually mean? Well, theorem is actually an ancient Greek word, and it basically means proposal. And in math, we call things that we think are true, that we have proofs for, theorems, right? They're saying, okay, we think this is likely true, so we're going to call it a theorem. Well, that's just one half. What does this Pythagorean half mean? That's a very, very long word. Well, Pythagorean actually refers to a person, Pythagoras. Now, who was Pythagoras? Well, Pythagoras was an ancient Greek mathematician who, as you might imagine, discovered the Pythagorean Theorem. In fact, why we call it the Pythagorean Theorem, why we use an ancient Greek word, is because Pythagoras himself was an ancient Greek, and so he'd likely call what he found a theorem. But enough of all that chatter. What is the actual Pythagorean Theorem? Pythagoras discovered a very, very interesting property of triangles, that really stumped him. Now, I'm going to explain this as he discovered it. We have to remember, the ancient Greeks didn't really have a concept of algebra, at least not like we do. They didn't know algebraic equations and systems of equations. Instead, they would say what they were doing through words, right? Essentially, geometry word problems. The Greeks loved those. So, here is, at least in words, what Pythagoras discovered. If I have a triangle, and it has a right angle, 90 degrees. Remember, this little half square is our right angle notation. And squares are made on each of the three sides. So basically what that means is I'm going to take this side and make a square out of it. I'm going to take this side, make a square out of it. And I'm going to take this side, make a square out of it. Then the biggest square has the exact same area as the other two squares put together. Now you might be saying, what on earth do you mean? Well, it's a great question. Let's say we were building a right triangle and it had a side length of 3, 4, and 5. Well, this means that this square, right, it has a length of 3, and it's because it's a square, it has a width of 3. So the area of this square is 3 times 3, or 9. This has a length of 4 and a width of 4, because it's a square. So this has an area of 16. This has a length of 5 and a width of 5. So it has an area of 25. 5 times 5. And if we add the areas up, 9 plus 16 equals 25. The sum of these two squares is equal to the area of this square. Very, very strange relationship. Now, we can take this and use some good old-fashioned algebra to put this in words that would be probably more familiar to you. So let's say we have side lengths A, B, and C. Right, where A is, in this case, 3, B is 4, and C is 5. All right? What we're really saying is, well, A times A, because that's the area of this square, plus B times B because that's the area of this square, is equal to c times c. What's another way to put this? Well, I see that I'm multiplying a variable by itself. That means I'm squaring it. So I can also say a squared, a times a, plus b squared, b times b, equals c squared, c times c. And this is Pythagorean theorem. A very, very interesting relationship. I mean, you wouldn't expect if you were just building squares, you would get this perfect alignment, that this square plus this square always equals this square, if it's a right triangle. Now, let's add in some other terms and notation, right? The longest side of the triangle, RC, we have a special name for because it's a pretty important property, right? This squared equals the other two sides squared. Well, in this right-angled triangle, the longest side is called the hypotenuse. As you might guess, it's another ancient Greek word because the ancient Greeks sure did love geometry. So, in a right-angled triangle, to put it another way, to put it in words, in a right-angled triangle, the square of the hypotenuse, this 5 or this c, is equal to the sum of the squares of the other two sides. So, a squared plus b squared. Now, I encourage you to pick whatever way you feel most comfortable with memorizing this formula. If you like thinking, oh, if I build squares off the sides of a right triangle, the Pythagorean theorem tells me that these two squares will be equal to this square. Or maybe you like the word version. The square of the hypotenuse is equal to sum of the squares of the other two sides. Maybe you say, okay, that's all messy, I don't like that. And you find with the algebra, a squared plus b squared equals c squared. I will say though, if you're memorizing this, be sure to know that the c squared is the hypotenuse, or the longest side. If we change this up, right, we say, okay, well, in this case, c is going to be 3, b is going to be 5, and a is going to be 4. Well, we're not going to get the same thing. The theorem is going to be true. This only works if we have c be the hypotenuse, or the longest side. So, how do we actually use it? Where are we going to see this pop up in problems? Well, all the time. The most common example is finding an unknown side. All right, say I'm given a triangle like this. I have a right angle here, so I know right away it's a right angle triangle. The Pythagorean theorem works for right angle triangles and no other triangles, so I can use the Pythagorean theorem. And this side is 5, and this side is 12. And I say this side is c. They want you to find c. Well, what do we know? We know we can use the Pythagorean theorem, and that's a squared plus b squared equals c squared. And we actually know both a and b. We don't know the hypotenuse, the longest side, which is c, so that's what we're trying to find. And now we'll do the math. That's 25 plus 144 equals c squared. That comes out to 169 is equal to c squared. And here we actually have to take the square root of both sides just to get c. And we get 13 equals c. So that's the earliest, most common use of the Pythagorean theorem, just to find missing side lengths. So we also can do some more practice with this. This time, let's say we know the hypotenuse, but we don't know something else. Say we have a triangle like this. Right, we know it's a right triangle, so the Pythagorean theorem is legal. In fact, if you're given a problem like this, the instant I see this right triangle symbol, this right angle, I would write a squared plus b squared equals c squared. Because I know it's a right triangle, I may have to use the Pythagorean theorem somewhere. And we're told that this is 9, and this side length is 15, and this side length is b. And we want to find b. Now, we know that this side is the longest side, right? It's the side opposite the right angle. That means it's the longest side. So we know that C is 15. We can just say, well, 9 is going to be A, so we have 9 squared plus B squared equals 15 squared. 9 squared is 81, B squared is B squared, and 15 squared is 225. So, we want to solve for B squared, or B. So that means we have to get B squared by itself. I'm going to subtract 81 from both sides. I'm left with B squared equals 144. I'll take the square root of that, and I get B equals 12. Just like that, I have found the length of this side. It is 12. Now, we can actually use the Pythagorean theorem in problems that don't have anything to do with triangles. You might say, well, how on earth do I do that? Well, let's think about a square. Right? A square is very clearly not a triangle. And to make this simple, I'm going to have this be a unit square, where all the lengths are 1. Now, here's where I need to use the Pythagorean theorem. Let's say I want to find the diagonal distance across a square, across this square. Now, here's where the Pythagorean theorem comes in. I've actually split this into 2 triangles. We know that a square has angles of 90 degrees, so we know that this is a 90 degree right here. So if we were to actually separate this out, right, I actually have a right triangle problem. I'm given this side length is 1, this side length is 1, and I want to find this side length. Perfect. We can use the Pythagorean theorem. We know that our diagonal, this dotted line here, this question mark here, is going to be our hypotenuse. It's the longest side, and it's the side opposite the right angle. And we know that our A and our B are 1. So we have A squared plus B squared equals C squared. Or in our terms, we have 1 squared plus 1 squared equals question mark squared. I could just use C, but I like keeping the question mark. Right? That's just 1 plus 1, or 2, equals question mark squared. Take the square root of that. I get the square root of 2 is my diagonal. So this right here, that diagonal, is the square root of 2. And that's what the Pythagorean theorem becomes more than just a party trick. We can take a variety of shapes and cut them up into triangles. And often we'll have right triangles. And there, the Pythagorean theorem can be incredibly useful at finding out the lengths of sides on those triangles. Last but not least, there's something else I'd like to share about the Pythagorean theorem. Something I particularly enjoy. So for a while I've been talking about the ancient Greeks, Pythagoras, who this relationship is named after. The Pythagorean theorem is one of very, very few relationships in mathematics that have been found absolutely everywhere. Ancient Indian mathematicians were writing about the Pythagorean theorem. So were ancient Chinese mathematicians. Einstein had a proof with the Pythagorean theorem, and so did our president, Andrew Garfield. Seems pretty crazy, right? Everyone was talking about the Pythagorean theorem. Why? Because it's pretty simple, but it's also pretty unusual, right? You wouldn't think that building a right triangle would have a squared plus b squared equals c squared for every single right triangle you could draw. And as a result, there are infinitely many people coming up with theories and proofs for this Pythagorean theorem. Here's one I particularly enjoy. And I'm choosing to end the video by this to kind of get our geometry skills into full practice. We'll be using all our areas and formulas for this one. So, this proof starts by basically saying, okay, say I have a square. And inside it, I have another square. A smaller square, of course, because we fit inside this. Positioned like this. Right? And since these are both squares, I know that, all of my square angles are going to be right angles. So this is going to be a right angle. 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 So is this and this. All right, and I'm going to label my my smaller square sides C. This is C, this is C, this is C, this is C. And I noticed that my smaller square sort of splits my my bigger square into basically two equal parts, right? But so I can say that this side length, which I'm going to call A, is equal to this side length, and this side length, which I'm going to call B, is equal to this side length. And this side length is A. This side length is B. A, B. And so on and so forth. Actually, this should be like that. Now, why is it the case? Well, that's because our squares obviously have the same side length for every single side. And so when that side length splits a square, it splits it into the same equal parts. Right, so AB, 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 AB. Well, what are we going to do now? Well, we see we actually have 4 triangles that we formed from this. We can say the area of one triangle is 1/2 base times height, or AB. The area of the large square is A plus B times A plus B, or A plus B squared. And the area of the small square is, well, C times C, or C squared. Well, putting this all together, we know that the large square, right, we get the large square by taking the small square's area and adding it to the area of our 4 small triangles. So let's write that in algebraic form, right? A plus B squared, the area of the big square, is equal to the area of the triangles, of which there are 4. So 4 times 1/2 AB plus the area of the small square, which is C squared. Right, let's write that in algebraic form. So let's put this apart and simplify. A plus B squared is A squared plus 2AB plus B squared. This is 4 times 1/2, or 2AB. And this is C squared. Well, if I subtract 2AB from both sides, I'm left with, I'm going to bring it up here, A squared plus B squared equals C squared. So boom, I've proved the Pythagorean theorem. For any right triangle whatsoever, A squared plus B squared equals C squared has to be true, right? Thanks to this shape. And this is actually a very, very old proof. This comes from an Indian mathematician and philosopher in the Middle Ages. And he found this relationship. And he just drew this picture. He didn't do any of the algebra. And he wrote below it, "Behold!" in big capital letters. Because this was a mystical thing, right? He was able to draw a picture. And from that picture, prove the Pythagorean theorem. And this is kind of explains why so many people and so many cultures and time periods have looked at the Pythagorean theorem. Because it's really a fascinating thing. But anyway, that's the Pythagorean theorem. A squared plus B squared equals C squared, where C is the hypotenuse, or the longest side, opposite the right angle. Now, I hope you found this lesson interesting. I know I did. And get ready for more lessons on triangles, because believe me, if you thought the Pythagorean theorem was pretty unique and out there, just wait until you find out what other stuff right triangles are hiding. But that's all. I hope you have a great day, and I hope this helped.